Okay, so now we're at the point where we can hope to solve the problem we posed at the beginning. And just to remind you what that looked like, if I draw some coordinate axes like this, then we start at the point P with coordinates A and YA, and we have another point Q with coordinates B and YB. And we think of drawing a curve between them, and we call that curve y of x. And we're not interested in the behavior outside of that range, but it can have any behavior it likes. And we're trying to find the function y of x that minimizes the traversal distance along that curve. And the way we posed that problem before in a mathematical form that's amenable to a, a unique, hopefully unique solution, was we wrote the functional capital S for distance of y was equal to the integral from a to b of the square root of 1 plus y prime squared with respect to x. And of course, this thing here is our f of x. This thing here is our f of y, y prime, and x. And this is what's going to appear in the Euler-Lagrange equation. Well, without further ado, let's just go on and solve the problem. So we have f is equal to root 1 plus y prime squared, and we aim to solve the Euler-Lagrange equation for this problem, which is the statement that df dy minus the total derivative of df dy prime, that should vanish. So this tells us we need to compute first df dy, trivial. It has no y dependence whatsoever, it only depends on y prime, therefore the partial derivative of f with respect to y vanishes. Now df dy prime is a bit more involved, because really we're trying to differentiate with respect to y prime 1 plus y prime squared to the half, and this has just got to be a half of 1 plus y prime squared to the minus a half, so we've multiplied by the power and reduced the power by 1, and then we multiply the whole thing by the derivative of the inside with respect to y prime using the chain rule, so that's times 2 y prime. We can cancel the factors of 2, and then when we simplify, we're going to come out with just y prime divided by the square root of 1 plus y prime squared. Okay, and really we just need to substitute these things into the Euler-Lagrange equation, so we put them in now, and we're going to have 0 for df dy minus the total derivative of df dy prime, which we just worked out was y prime over root 1 plus y prime squared. All that's got to be equal to 0. And of course, you can probably see this is just the same as the statement that the derivative with respect to x of y prime over root 1 plus y prime squared has just got to be equal to 0. Now, clearly, this is just a statement that y prime over root 1 plus y prime squared, what's that got to be equal to? It'll equal to some constant k, so k, which is a constant, right? And that's just clearly the same as the statement that its derivative is 0. The derivative of what is 0? A constant. What constant? Any constant, right? So now to continue, well, let's solve this equation, because the goal is here, there's a y prime here and a y prime here, so really we'd quite like to collect them together before we begin solving the differential equation. So we multiply through by that root 1 plus y prime squared on the bottom, and we'll come up with y prime is just equal to k lots of 1 plus y prime squared. We square both sides, and to get rid of the square root, and we'll come up with y prime squared is just k squared 1 plus y prime squared, which is just k squared plus k squared y prime squared. Now if we just move all of the y prime squareds to the left-hand side, we're going to come up with y prime squared times the contribution of 1 from this side minus the k squared from that side. So this came from here, and this came from here. Then we're just going to have that's going to be equal to k squared, which is what's left over. And of course, well, we're within our rights, just write y prime is just equal to the square root of k squared over 1 minus k squared. So the square root of that. Particularly it's plus or minus that. But this thing k, we said that was a constant, remember? So the square root of k squared over 1 minus k squared, that's just another constant that we'll call m. Okay. So, well, we have y prime is equal to m, so the derivative is equal to m, and if we integrate that, what we're going to find is y is just equal to mx plus some constant. And this is just the equation of a straight line. So we've proven what we set out to prove. We've literally just shown, without a shadow of a doubt, that the function, the curve y of x that makes the distance between these 2 points stationary is a straight line. Y equals mx plus c.